The commercialization of next-generation high-temperature gas-cooled reactors faces an immediate physical constraint. The rate-limiting step is not reactor construction, but the fabrication of tristructural isotropic, or TRISO, fuel. Cumulative fuel demand is projected to reach 150 metric tons of heavy metal by 2032. However, Western fabrication capacity, led by BWXT and X-Energy, will only reach 15 metric tons per year by that date. This mismatch creates a persistent structural deficit throughout the decade. A single 320 megawatt thermal reactor requires an initial core load of 15 metric tons. This single startup load consumes 100% of the entire projected Western fabrication capacity for 2032. The supply chain cannot support simultaneous multi-reactor deployments. The manufacturing bottleneck is rooted in the physics of fluidized bed chemical vapor deposition. Applying 4 distinct microscopic coatings to uranium kernels requires extreme thermal precision. The silicon carbide deposition stage operates at 1500 degrees Celsius using highly corrosive methyl trichlorosilane gas. This step has an individual yield of 89.0% due to single-digit micrometer tolerances. Cumulative material yield loss across all stages reaches 36.8%. Consequently, producing 1.0 kilogram of qualified TRISO fuel requires 1.58 kilograms of raw uranium feedstock. Furthermore, fluidization instabilities in the coating chambers limit batch sizes to just 5 to 10 kilograms. This physical limit prevents the economies of scale typical of conventional nuclear fuel fabrication. This fabrication bottleneck is compounded by an upstream feedstock monopoly. TRISO fuel requires high-assay low-enriched uranium, enriched to between 5 and 20%. Russia's Statone 10X controls over 95% of current global commercial supply. This creates an acute geopolitical vulnerability for Western reactor developers. Domestic United States capacity at Centrus Energy is limited to a demonstration cascade producing less than 1.0 metric ton per year. Scaling Western enrichment capacity to 21.0 metric tons by 2030 requires at least $2.5 billion in capital investment. Without this infrastructure, the transition to advanced gas-cooled reactors remains entirely dependent on foreign state-controlled monopolies. This vulnerability mirrors the early industrial scaling hurdles of the Manhattan Project.